All right, welcome to this lecture on the Doppler effect. Now, before we discuss the Doppler effect for electromagnetic waves, let's first review what we've learned in introductory physics for the sound Doppler effect. So in the case of sound, we have a source of sound waves, which is emitting sound waves in these outgoing spheres, if you like. And we have a detector, perhaps your ear, listening for those sound waves. But the source may move at some speed relative to the air, as can the detector. Now, what is the Doppler effect? Well, that is a change in pitch, that is a change in the frequency of a sound wave due to the motion of the source emitting the sound waves and or the motion of the detector receiving them. So if either move, it will change the pitch that you hear relative to the pitch in the reference frame of that emitter, that source. Now, sound waves propagate in the reference frame of the air at the speed of sound, which at standard temperature and pressure is 343 meters per second. So the velocities are always with respect to the air that the sound waves propagate in. And the perceived frequency depends on the motion of the source and the receiver. How does it depend? Well, what we've learned from introductory physics is that the detected frequency, let's call it f prime, is the emitted frequency in the frame of the source, f, and then times this ratio. V is the speed of the sound in the air, and then it's plus or minus velocity of the detector in the air divided by v plus or minus the velocity of the source in the air. Now, how do I choose the plus or the minus in these relations? And they don't have to be the same. If you choose plus in the numerator, it doesn't necessarily mean plus in the denominator. Well, we go by the qualitative features of the Doppler effect, which is that we increase the frequency if the source or detector move toward each other. If I hear the sirens from an emergency vehicle coming toward me, the pitch will appear slightly higher as it's coming toward me. As it passes, the pitch will go down, so we decrease the frequency if the source or detector move away from each other. And it doesn't really matter which way, who's moving relative to the other, the pitch goes down as long as one is moving away from the other. But we do have to choose where in the numerator denominator. So if it's the detector that's moving, maybe you're driving by, if you're coming towards something, I would choose a plus in the numerator. However, if it's the source which is coming toward me, I would choose the minus in the denominator. Both of those, a small number in the denominator will increase the frequency, or a larger number in the numerator will also increase the frequency. And you choose the opposite case if the source or detector are moving away from each other. Detector's moving away, the frequency goes down. I would choose a minus in the numerator. If it's the source that's moving away, I would choose a plus because both of those will give me a lower frequency f prime. Okay, that was for sound. But now we want to talk about electromagnetic waves. Right? So I've got some wave here. It's sinusoidal in shape. I have a source here emitting the sound waves. They travel at the speed of light. Not sound waves, they're emitting electromagnetic waves, moving at the speed of light. And this is plotting, say, the magnitude of the electromagnetic field as a function of time and distance. So the question is there a Doppler effect for EM waves in the absence of an ether, right? Electromagnetic waves don't need air to propagate in. They don't need anything. Everyone in an inertial frame measures the same speed of the wave, c. So maybe there's no Doppler effect at all, right? So that's what we want to explore in this lecture. So let's consider an electromagnetic wave traveling along the x-axis. So it's going here to the right, the horizontal direction, we'll call that the x-axis. And the source starts emitting the waves, we see them moving here toward the right. Okay? All right, let's say the source emits n wave crests, that means n of these peaks, in a time t0 in the inertial frame of the source emitter. So we're essentially in the rest frame of the source, and we're going to emit n wave crests in a time t0. So the first wave crest that's received by the receiver, we'll call that crest 1. The last one will be crest n. There it is, and it's coming toward the receiver. Okay, so we'll count n of them in a time t0 in the frame of the source. We will define the wavelength lambda naught, and that's basically just the peak-to-peak distance between, or trough-to-trough between crests or troughs in this wave. And the speed, of course, of the electromagnetic waves is the speed c. Now the length of the wave train, L naught, will be however many wave crests we have, n, times the wavelength at lambda naught. But that also has to be the speed of which the wave propagates times the total time t naught over which they were emitted. That will be the whole length of the wave train from crest 1 on the one side and crest n on the other. That total length in the frame of the source is just c times that time, which is n wavelengths, n lambda naught. Now, how is lambda naught defined? That would just be the total length divided by n wave crests. So, yeah, if I had n wave crests, then just take the total length divided by n, and that's the length of any one of them, peak-to-peak distance. And then we can use a feature which has come for all waves, which is the wavelength times frequency is equal to the speed of the waves, which for EM waves is c, the speed of light. So lambda times f equals c. And so we can solve this, use this relation to get the frequency. The frequency is just c over lambda. So here's c, and then our wavelength in the rest frame is lambda naught. But lambda naught we just worked out to be ct naught over n. So we put the ct naught in the denominator, n times c in the numerator. The c's will cancel. That c cancels with this c. I just have n over t naught. In other words, the frequency is just the total time divided by n, and then 1 over that. All right, does that make sense? Hopefully. Okay. All right. Now, let's consider a receiver in a different inertial frame from the source. So I've got my source emitting waves, right? The waves will move at speed c, but now let's let the source move across the screen at some speed v toward my receiver. And let's see if that leads to a change in the frequency. So again, we want to compute the frequency, but now as it's received by the receiver from the length of the wave train we observe in the receiver's reference frame. So we're going to do the same trick. We're going to count n wave crests, because that's a number we can all agree on. And then we'll say n times the wavelength we observe in this frame must be the length of the wave train. Right? N times the wavelength. So the wavelength, again, is the peak-to-peak difference, or trough-to-trough. Now, you might think the length is just c times t, the total time they're emitted. But remember, from the time the first crest is emitted and travels to the receiver, the last crest, n, didn't have to travel as far. It was moving at speed v toward the receiver as well. So the total length gets squished a bit. It's not ct, but it's ct minus an extra amount, which is the velocity times time, if the source is moving toward the receiver. So it's minus v times t for that total length. If the source were moving the opposite direction to the left, then I would choose plus, because now the wave train is being extended. Okay? So you choose the minus in this expression for the source approaching the receiver, and the plus if it's receding, moving away from the receiver. So using that, we can solve for lambda. Lambda is just 1 over n times this expression here. So I can factor out the t. Here's the t. There's my 1 over n. And then I just have c minus plus v. And the frequency, therefore, is just c over the wavelength. That's the wave relation for frequency times wavelength. And so it's I invert this expression here. The n goes in the numerator. It's multiplied by c. And then the c minus plus v goes in the denominator. And the t goes in the denominator. Okay, so we might say we're done, except that this t is as measured in the receiver's reference frame, right? Not the reference frame of the source. Now remember, special relativity tells us there's a time dilation effect. That the time we measure in the receiver's frame is different than that in the emitter's frame by the Lorentz factor gamma. It gets stretched out. So this might help give us some change in the expression for the frequency as well. So let's take into account time dilation. Okay, so what do I do here then? That t in the equation above, we might replace with gamma t naught. So here's my gamma, there's my t naught for the t here. There's the c minus plus v from there. and then there's the Cn from over here. So that's true. Now, the n over t naught, that's what we call in frequency on the previous slide. So that's f naught, right? 1 over the total time divided by n. And then the c I can absorb in the denominator and just call this 1 minus plus v over c. So there's 1 minus plus v over c. And then I have that factor gamma out there. And I see the emergency vehicles nearby me are deciding to test out that Doppler effect in the air, if you can hear that in the background. Okay. All right. Let's go ahead and do some math expanding out that Lorentz factor gamma. So here we go. Number gamma is 1 over the square root 1 minus v squared over c squared. But if it's in the denominator, that square root comes up in the numerator here, square root 1 minus v squared over c squared. So that's the 1 over gamma. There's f naught. And there's 1 minus plus v over c. But this 1 minus v squared over c squared, that's like a product of binomials. That's 1 minus v over c times 1 plus v over c. And that can be convenient because written that way, in the denominator, the 1 minus plus v over c can cancel one of those binomials partly, because this is to the first power, that's to a 1/2 power. So we can write the expression slightly differently. We're not really changing the answer. We're just recasting this so we can put everything under the radical. So let's do that, and I'm going to switch slides then. And let's discuss the source and receiver approaching each other. And here we go. So I put that, cancel one of those binomial terms. Everything's under the radical. 1 plus v over c, 1 minus v over c times the frequency f naught. That's the frequency in the reference frame of the source, is the frequency I receive. So this is if they're approaching each other. And remember we said if they're approaching each other, frequency, at least in air, would typically increase. And here's the same thing. If the source and receiver are approaching each other, f is greater than f naught because we've chosen the negative in the denominator and plus in the numerator. So it's 1 plus v over c over 1 minus v over c. And if you go to higher frequency, if it were light, you tend to go to the blue end of the spectrum, higher frequency. So we call that blue shifted if you are the source or receiver are approaching each other. Frequency goes up. If the source and receiver recede from each other, then the signs are inverted, and the numerator has a minus, 1 minus v over c, and it's over 1 plus v over c times f naught. And that's going to give you a lower frequency. It's redshifted. Sorry, well, which is referred to as redshifted because if you're shifting optical light, going to lower frequency means you're going to the red end of the spectrum. So it's a lower frequency you've received. So blue shifted means higher frequency, red shifted, lower frequency. And these are the equation. It really only depends on the relative velocity of the two frames, not on the velocity of any of the source or detector with respect to some frame like the ether. There is no ether. There's just relative velocities between these two objects. So at some level, this equation, although it's not the same as the equation for the Doppler effect of sound waves, it's simpler because you have one less velocity to deal, or two less velocities to deal with. You don't have the source and detector separately along with the speed relative to the air. You just have the relative velocity between the two. Okay, some comments about the Doppler effect for electromagnetic waves. That change in frequency is observed and can actually be put to use. And one thing about modern electronics is it allows us to make precise measurements of frequencies. So that equation on the last slide we just saw with the square root of the 1 plus or minus v over c over 1 minus plus v over c, we can solve that for the velocity of an object from the change in frequency between emitted electromagnetic waves and those waves received after reflection off of an object. Or maybe it's just an object emitting them. So if we know what the natural frequency is, say of a radio transmitter, and then that transmitter is either coming toward us or away from us, and the frequency we measure is different, from that difference in frequency, we can solve for the velocity. And so essentially that's how a police radar gun works, trying to measure the speed of vehicles coming toward or away from it. It's bouncing electromagnetic waves off of them, and from the change in the frequency can infer the velocity. You also may have heard about Doppler weather radar, right? When we're, especially in Florida, if there's thunderstorms or storm fronts coming by. You want to know, well, how fast are those storms coming? How fast is the raindrops in the clouds moving? Again, you're emitting electromagnetic waves. They're bouncing off, and you can, by the change in frequency, solve for the speed, right? Scientifically, even more interesting, distant galaxies tend to be receding from us. So the velocity of those distant galaxies relative to our galaxy can also be measured by comparing the frequency of known atomic light frequencies. For example, later in this course we'll learn about emission at specific frequencies from atoms. We can see how those frequencies change and solve for the velocity of that galaxy. And they all tend to be lower in frequency, they're redshifted, and that is evidence for the Big Bang, that the universe is expanding. All right. So just some examples of how you can put this to use. Now, just one comment. When you are emitting electromagnetic waves and they reflect off of an object like the police radar does or the Doppler weather radar, note that this is actually two effects. It corresponds to the Doppler effect twice. In one case, you are emitting the waves and they're going to be detected, if you like, by the vehicle or the object. In other words, they're going to hit the surface, they're going to be absorbed. And then that source re-emits the waves in the opposite direction. So there's both a receiving by the source, by the detector, and then that detector becomes a source and re-emits them, it reflects them. So there's actually, you have to apply the Doppler effect twice if you solve a problem that way. All right, let's do a simple example of the electromagnetic Doppler effect. All right, so it's going to be an example with a traffic light. How fast do you need to travel to make a red traffic light appear green? All right, how fast do you need to travel? Change the color of the light. Now I need to give you some information. Red lights, or at least the red color, has a wavelength of about 700 nanometers. And the wavelength of green light is about 550 nanometers. And recall we have the wave speed relation, frequency times wavelength is the speed of light for electromagnetic waves. Now, to make it appear green, that's going to go to a smaller wavelength, that's a higher frequency. So we need to have the car travel toward the traffic light. So traveling toward means the light is blue shift. It goes to the blue end of the spectrum, higher in frequency. So, again, we're going to want to solve for that velocity. Remember I told you you can invert this equation that we gave for the Doppler effect. So we want the frequency of green light over the frequency of the red light. But that's the inverse of the wavelengths by this relation here. So that's frequency of green light is c over the wavelength of the green light. Frequency of the red light is c over the wavelength of the red light. And I'm just going to have the wavelength of the red light over the wavelength of the green light. And then from the Doppler formula, I choose the values, the plus and minus, such that I get a larger number because the frequency has increased. So I have 1 plus v over c in the numerator, 1 minus v over c in the denominator. That's the equation I need to invert and solve for v. So we're going to do that. I've done it quickly, so you may need to pause the video or at least offline, see if you can work this out. But I'm going to square both sides. Well, actually I'm going to square the side of lambda red over lambda green. That gets rid of the radical. Then I multiply both sides by 1 minus v over c. Right? And then I have some algebra to rearrange the v over c terms on one side and everything else on the other. And that's what I've done here. So it turns out the v over c is the wavelength of the red light over the wavelength of green light, quantity squared, minus 1, over the wavelength of red light over wavelength of green light, quantity squared, plus 1. And what you'll get is 0.24. In other words, if you want to travel fast enough so that the red light in a traffic signal looks green to you, you need to go at 24% the speed of light. But if you do, you have a legitimate excuse. You can say, sorry, officer, the light looked green to me. and you would be correct. All right, that ends this lecture on the electromagnetic Doppler effect.